start with something familiar. Step outside on a clear night, far from the city, and look up. You already know the stars you see belong to our galaxy. You already know the universe is large. You've heard the word billions attached to distances so many times it has stopped landing with any real weight. But there is a difference between knowing the universe is large and understanding what that largeness actually means. Tonight, we're going to close that gap. We're going to talk about the space between galaxies, what fills it, what shapes it, and why the distances involved don't just exceed human intuition, they defeat it entirely. By the end of this, the number 2.5 million light-years, the distance to our nearest galactic neighbour, will feel like what it actually is, and not just an abstraction. If you enjoy this type of content, consider liking and subscribing to the channel. It truly helps me. Now get comfortable. Let's begin. Every star you can see on a clear night exists inside the Milky Way. Every constellation, every naked eye object in the sky above you. All of it sits inside the same galaxy as our own Sun. Even the most distant star visible without a telescope is just a neighbour by cosmic standards, a few thousand light-years away at most. Our galaxy stretches about 100,000 light-years from one edge to the other. That number already exceeds anything human experience is built to hold, and yet it is almost nothing compared to what lies beyond it. Because the Milky Way doesn't exist alone. It exists inside a universe filled with other galaxies, each one an island of hundreds of billions of stars, separated from us by gulfs of space so vast that our entire galaxy would be a rounding error in the calculation. The nearest of those islands is the Andromeda galaxy, sitting about 2.5 million light-years away. That single number is already staggering, but let it settle in the right way. Light moves at about 186,000 miles per second. In 1 year, it travels roughly 5.9 trillion miles. 2.5 million light-years is approximately 14.7 quintillion miles. That is 14.7 with 18 zeros behind it, and Andromeda is our neighbour, the closest large galaxy to our own. When you look at it in the night sky, that faint smudge near the constellation Andromeda, you're seeing photons that left their source around the time our ancestors first began shaping stone tools in East Africa. The galaxy was already there, already ancient, already burning with hundreds of billions of stars. That light has been travelling through empty space ever since, crossing 2.5 million light-years of almost nothing to reach your eye tonight. 25 Milky Ways laid end to end would not quite bridge the gap to our nearest large neighbour, and Andromeda is close. By any honest measure of what this universe contains, Andromeda is practically in the same room. But before we can feel the weight of that distance, we need a reference point, something to stand on before the floor disappears. The Milky Way itself is that reference point, and it is worth spending a moment inside it before stepping beyond it. Picture the Milky Way as a flat disk, a spiral of stars roughly 100,000 light-years across, and a few thousand light-years thick at its centre. If you could somehow compress the entire galaxy down to the size of a dinner plate, each individual star would be smaller than a single atom. There are somewhere between 200 and 400 billion of them, spread across that disk in curving spiral arms that take hundreds of millions of years to complete a single rotation. Our Sun sits about 26,000 light-years from the galactic centre, roughly 2/3 of the way out toward the edge. It is not in any particularly remarkable location. It sits in a relatively quiet region between two spiral arms, orbiting the centre of the galaxy at about 500,000 miles per hour. At that speed, it takes our solar system roughly 230 million years to complete one full orbit around the galactic core. Astronomers call that unit of time a cosmic year. In the entire history of complex life on Earth, the solar system has completed barely 2 of them. The centre of the galaxy is a place of extraordinary density and violence. At its heart sits Sagittarius A star, a supermassive black hole with a mass 4 million times that of our Sun, compressed into a region smaller than the distance between Earth and the Sun. Around it, stars orbit at speeds of thousands of miles per second, whipping around the black hole in orbits that take only a few years to complete. It is the engine at the centre of our galaxy, largely hidden from view by thousands of light years of intervening dust and gas. And yet from our position, it is invisible to the naked eye. The entire centre of our own galaxy is hidden behind the plane of the Milky Way, blocked by the very disk we live inside. On a clear night, what you see when you look toward the constellation Sagittarius is not the galactic centre itself, but a dense brightening of the Milky Way's glow, the accumulated light of billions of stars stacked along the line of sight. The actual centre lies behind all of that, unreachable in any practical sense. This is worth holding on to. We live inside a structure so large that we cannot see its own centre with our eyes. A structure so wide that light would take 100,000 years to cross it from edge to edge. And this structure is the baseline unit of measurement for everything that follows. It is the yardstick we use when we say Andromeda is 25 Milky Ways away, and the yardstick itself is already incomprehensibly large. Now step back outside its edges. The Milky Way is surrounded by a vast diffuse halo of older stars and globular clusters, gravitationally bound collections of hundreds of thousands of stars packed into spheres just a few hundred light years across. There are over 150 of these clusters orbiting the Milky Way, relics of the galaxy's earliest formation, some of them nearly as old as the universe itself. The halo extends hundreds of thousands of light years beyond the visible disk in every direction. Orbiting within and around that halo are the Milky Way's satellite galaxies. The largest of these are the Magellanic Clouds, visible from Earth's southern hemisphere as bright detached patches of light. The Large Magellanic Cloud sits about 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years out. Both are being slowly distorted by the Milky Way's tidal forces, their gas drawn out into a ribbon called the Magellanic Stream that arcs nearly halfway across the sky. So when we talk about the distance to Andromeda, 2.5 million light-years, we're not talking about the distance from the edge of our visible disk to the edge of theirs. We're talking about the distance between the centres of two gravitational systems, each of which extends its influence hundreds of thousands of light-years beyond its visible stars. The space between them is not merely a gap between two objects, it is a region of the universe where almost nothing exists, where a spacecraft travelling at the speed of light would spend millions of years crossing near total emptiness before the glow of another galaxy began to resolve itself out of the dark. That is the distance to our nearest neighbour. That is the closest the universe has placed another large galaxy to our own. And the number is already so large that no analogy fully survives contact with it. And here's what makes that distance remarkable. The space between us and Andromeda isn't empty in the absolute sense, but it is the closest thing to nothing that the universe consistently offers. Inside our own galaxy, the space between stars contains roughly 1 atom per cubic centimetre. That's not much by any standard, but it's practically crowded compared to what lies between galaxies. In the deep space between galactic clusters, the density can drop to less than 1 atom per cubic metre, sometimes far less than that. A cubic metre is roughly the size of a washing machine, 1 atom. In the most extreme voids, that density falls further still, to around 1 atom per 10 cubic metres. An atom about the size of a proton, 1/10,000,000th of a metre across, alone in a volume the size of a large wardrobe. For comparison, the air you're breathing right now contains roughly 25 million billion molecules per cubic metre. The intergalactic void contains 1. There is no human experience that prepares you for that ratio. There are regions out there where you could travel for millions of miles in any direction and never encounter a single particle. Not a hydrogen atom, not a photon of visible light from any nearby source. Just the ancient faint glow of the cosmic microwave background radiation, a relic from the birth of the universe, spread equally in all directions, filling the void with light so cold and stretched it can no longer be seen by human eyes. The cosmic microwave background has a temperature of about 2.7 degrees above absolute zero. That's barely a whisper above the coldest possible temperature in nature, and it fills all of intergalactic space uniformly. Every other radiation, every photon of starlight, every galaxy's glow thins rapidly with distance. But the cosmic microwave background is constant everywhere. It is the afterglow of creation, dimmed over 13.8 billion years of expansion to a temperature barely above nothing. This is what the space between galaxies actually contains. Not darkness in any familiar sense. Not the kind of emptiness you find in a quiet room or at the bottom of the ocean. Something categorically different. A vacuum so complete that the concept of emptiness as we normally use it no longer applies. The void between galaxies is not a place where things are absent. It is a place where the very idea of presence barely has meaning, and yet that near nothing is not without structure. It has a name. Astronomers call it the intergalactic medium, and understanding what it is made of, how it behaves, and what it records turns out to be one of the most revealing ways we have of reading the history of the universe itself. The intergalactic medium is overwhelmingly composed of hydrogen and helium, the two lightest elements left over from the Big Bang and never incorporated into stars or galaxies. In its densest forms, near galaxy clusters, it can reach a few atoms per cubic meter. In the vast cosmic voids, it thins to almost nothing at all. It is invisible to optical telescopes. Its density is too low, its temperature too variable. It exists as an extremely diffuse plasma, atoms stripped of their electrons, too thin to emit any appreciable visible light. To our eyes, and to any ordinary camera pointed at the sky, the intergalactic medium simply isn't there. It is a ghost filling the largest spaces in the universe, detectable only by the subtle marks it leaves on light passing through it. But in X-rays, portions of it glow with a heat of gas that has been compressed and shocked by the gravity of galaxy clusters. Around massive clusters, X-ray observations reveal vast halos of superheated plasma, tens of millions of degrees, spread across millions of light-years of space between the galaxies. This hot gas can contain more mass than all the visible stars in the cluster combined. The intra-cluster medium glows so powerfully in X-rays that massive clusters are among the brightest X-ray sources in the sky, outshining all the stars within them when observed at those wavelengths. The space between galaxies, invisible and seemingly inert, turns out to be one of the most energetic environments in the observable universe, just at wavelengths our eyes were never built to detect. In the ultraviolet, the intergalactic medium reveals itself in a different way entirely. As light from a distant quasar makes its billions of years journey toward us, it passes through countless clouds and wisps of intergalactic gas along the way. Each cloud absorbs a narrow slice of that light at specific wavelengths, corresponding to the hydrogen it contains. By the time the quasar's light reaches our telescopes, it carries encoded within it a record of every cloud of intergalactic gas it passed through on its journey. Astronomers call this record the Lyman Alpha Forest, named after the specific ultraviolet wavelength at which neutral hydrogen absorbs light. It is one of the most powerful tools we have for studying the large-scale structure of intergalactic space across cosmic time. Every bright quasar is, in effect, a lighthouse illuminating a column of the intergalactic medium stretching billions of light-years toward us. We can read that column like a barcode. Through this technique and others, we now know that the intergalactic medium is not a uniform fog. It is structured, tracing the same cosmic architecture that organizes the galaxies themselves. Along the filaments where galaxies cluster, the gas is denser and warmer, feeding material into the clusters at their nodes. In the voids, it is thinner and cooler, stretched across billions of light years with almost nothing to disturb it. The intergalactic medium is not separate from the large-scale structure of the universe. It is the large-scale structure of the universe, rendered in gas instead of stars, and threading through all of it, invisible but gravitationally dominant, is the signature of dark matter. Dark matter makes up about 85% of all the matter in the universe. It does not emit light. It does not absorb light. It does not interact with the electromagnetic force at all. But it interacts gravitationally, and that interaction alone is enough to shape everything we see. The filaments of the cosmic web, the walls, the voids, the clusters, all of it traces the underlying structure of dark matter that formed first, pulling ordinary matter in after it. Without dark matter, the intergalactic medium would have no web to trace. The galaxies would not have clustered in the patterns we observe. The architecture of everything would be fundamentally different. There is one more way the intergalactic medium has recently revealed itself, and it is perhaps the most striking of all. Fast radio bursts are extraordinarily brief, extraordinarily energetic pulses of radio waves that last only milliseconds, but release in that instant as much energy as the sun produces in days or weeks. When these pulses travel through the intergalactic medium, the plasma they pass through slows their lower frequencies very slightly more than their higher ones. The denser the plasma, the greater that delay. By measuring exactly how spread out the signal is when it arrives, astronomers can calculate how much intergalactic gas the burst passed through on its journey. It is a direct physical measurement of the void itself, not inferred from the light of galaxies, not modelled from theory, but stamped into the signal by billions of light-years of near-empty space. Using this technique, astronomers confirmed something that had been suspected for decades, but never directly proven. Roughly half of all the ordinary matter in the universe resides not in stars, not in galaxies, but in the intergalactic medium. Spread across the voids and filaments between galaxies, invisible to optical telescopes, too diffuse to show up prominently in X-ray observations, but measurable by the faint delay it imposes on a millisecond flash of radio waves crossing the void. The missing matter was there all along. It was hiding in the space between everything, waiting for us to find the right way to look. Now, to understand why intergalactic distances are what they are, we need to step back and look at the largest organised structure in the universe. Because the galaxies are not scattered randomly across space. They follow a pattern, and that pattern has a name. Astronomers call it the cosmic web, and it is the reason the space between galaxies takes the specific forms that it does, why some gaps measure millions of light years and others measure billions. In the very early universe, fractions of a second after the Big Bang, matter was distributed almost, but not quite uniformly. There were tiny fluctuations in density, regions that were ever so slightly denser than average, regions that were fractionally more empty. These differences were incredibly small, on the order of 1 part in 100,000. You could have measured the temperature of the universe in 2 different places and found a difference smaller than the width of a human hair compared to the distance across a city. And yet those differences were enough. Gravity seized them and never let go. Over hundreds of millions of years, gravity amplified those tiny imbalances relentlessly. Dense regions pulled in surrounding matter, becoming denser still. Less dense regions lost matter to their neighbours, becoming emptier. Over billions of years, this process organised all the matter in the universe into something that looks, at the largest scales, like a vast 3-dimensional web. filaments of galaxies stretching for hundreds of millions of light years. Nodes where filaments intersect, forming dense clusters containing hundreds or thousands of galaxies. And between the filaments, enormous empty regions called cosmic voids, the dominant feature of the universe by volume. The cosmic web is not a metaphor. It is a physical structure mapped across billions of light years by surveys like the Sloan Digital Sky Survey and the 2-micron All-Sky Survey. What those surveys revealed, over and over, is that the voids dominate. The filaments and walls and clusters of galaxies are spectacular, but they are thin. They are the edges of bubbles, not the bubbles themselves. The voids, the emptiness, make up roughly 80% of the universe's total volume. 8 out of every 10 cubic light-years of space contains effectively nothing. No galaxies, no star-forming gas, no stellar nurseries, just the faintest whisper of the intergalactic medium, a plasma so thin it would register as a near-perfect vacuum by any laboratory standard on Earth. Our own Milky Way belongs to a small collection of galaxies called the Local Group. The Local Group contains somewhere around 80 galaxies in total, though most are small dwarf galaxies orbiting the two giants, the Milky Way and Andromeda. The full span of the Local Group stretches roughly 10 million light-years from one edge to the other. 10 million light-years of galaxies, dwarf galaxies, satellite galaxies, streams of stripped stars and gas bridges all gravitationally bound together. And then beyond the edges of the Local Group, the distance to the next significant galaxy cluster is vastly, incomprehensibly larger. The nearest major cluster to the Local Group is the Virgo cluster. It sits roughly 50 million light-years from us. Between the outer edge of the Local Group and the Virgo cluster, there is a gap of around 40 million light-years. 40 million light-years of intergalactic space. If you travelled that distance at the speed of light, you would cover 186,000 miles every single second without stopping, without slowing, for 40 million years. The Sun would exhaust its hydrogen fuel and expand into a red giant during a journey like that. The solar system would be transformed beyond recognition before you arrived. And that is just the gap between two relatively close structures on a cosmic scale. The Virgo cluster itself is a massive concentration of over 1,300 galaxies. It is dominated by 3 giant elliptical galaxies, the largest of which is Messier 87. At the centre of Messier 87 sits a supermassive black hole with a mass of about 6.5 billion times that of our Sun. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, and it was this black hole, 60 million light-years away, that they imaged. The resolution required to achieve that was enough to resolve a feature the size of a golf ball on the surface of the Moon. That result, directly imaging a feature of a black hole across 60 million light-years of intergalactic void, is a testament to what becomes possible when you understand the space between galaxies rather than treating it as an obstacle. The Virgo cluster is the gravitational heart of the Virgo supercluster, which spans about 110 million light-years and contains dozens of galaxy groups and smaller clusters, including our own Local Group. And in 2014, a team led by astronomer Brent Tully mapped the motions of thousands of galaxies across a vast region of space and found something remarkable. Galaxies aren't just moving apart with the expansion of the universe. They also have small deviations from pure expansion, caused by the gravitational pull of nearby mass concentrations. By tracing where galaxies were being pulled toward, the team could map the boundaries of gravitationally connected structures. What they found was that the Virgo supercluster, along with several other nearby superclusters, are all part of a single enormous structure. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 500 million light-years and contains about 100,000 galaxies. The Milky Way sits on its outermost edge. At the centre of Laniakea is a region of unusually concentrated mass about 200 million light-years away, known as the Great Attractor. For decades, astronomers knew something massive was pulling on the local group, but the Great Attractor lies behind the zone of avoidance, the part of the sky blocked by the plane of our own galaxy. All the dust and gas in the Milky Way's disk hides what lies directly behind it in optical light. Only using infrared and radio observations, which can penetrate the dust, have astronomers been able to map this hidden region. The Great Attractor turns out to be a complex of multiple galaxy clusters, all gravitationally bound together, drawing in surrounding galaxies at speeds of hundreds of miles per second. And even the Great Attractor isn't the end of the gravitational story. Beyond it, the Shapley supercluster sits about 650 million light-years away. It is one of the largest concentrations of matter in the nearby universe, containing over 8,000 galaxies organized into dozens of individual clusters. The Shapley supercluster is tugging on Laniakea, adding its gravitational influence to the complex flow of galaxies across our local region of the cosmos. And beyond the Shapley supercluster, the cosmic web continues, filament after filament, void after void, cluster after cluster, all the way to the observable horizon at 46.5 billion light-years. Each step outward multiplies the previous scale by a factor that wipes away whatever foothold your intuition had just found. The local group is to Laniakea what a single house is to an entire continent. Laniakea is to the observable universe what that same house is to the entire surface of the Earth. The numbers stop being numbers at some point. They become something else, a succession of thresholds, each one dissolving the one before it, until what remains is not a quantity you can hold but a direction you can only gesture toward. That is the cosmic web, not a backdrop to the universe, a living record of its entire history, written in the arrangement of matter across the larger scale space permits. Now there is another dimension to all of this that changes everything. The distances we have been describing are not fixed. They are not stable measurements you could check today and find the same tomorrow. The space between galaxies is expanding, not the galaxies moving through space in the ordinary sense of something hurling itself from one place to another, but space itself stretching, the fabric of the universe growing, carrying galaxies apart the way raisins in a rising loaf of bread are carried apart even though none of them moves through the dough. Edwin Hubble demonstrated this in the 1920s. By measuring the light from distant galaxies, he found that almost all of them showed a redshift. Their light had been stretched to longer, redder wavelengths during its journey to us. And the farther the galaxy, the greater the redshift. This was the observational signature of an expanding universe. The discovery did not just change astronomy, it changed the entire human conception of what the universe is. The cosmos was not a static, eternal arrangement of stars and galaxies sitting in fixed positions. It was a dynamic, evolving structure, growing larger with every passing second, its contents being carried apart by the expansion of the very space they inhabit. This expansion has enormous implications for what we even mean when we talk about intergalactic distances. When we say a galaxy is 1 billion light-years away, we mean its light has been travelling for 1 billion years to reach us. But during that 1 billion years of travel time, the universe has been expanding. The galaxy that emitted that light 1 billion years ago is now farther away than it was when the light left. How much farther depends on how fast space has been expanding throughout that entire interval. For nearby galaxies, the difference is small enough to ignore. For distant ones, it becomes dramatic. Astronomers use different measures of distance for different purposes as a result. The light travel distance, also called the look-back time, measures simply how long the light has been travelling. The comoving distance accounts for expansion, measuring how far an object is in the universe's current configuration. For nearby objects, these numbers are similar enough to treat as equal. For distant ones, they diverge dramatically. The most distant galaxies ever detected by telescopes like the James Webb Space Telescope emitted their light when the universe was only a few 100 million years old. Their light has been travelling for over 13 billion years. But those galaxies are not 13 billion light years away from us today. Because space has expanded during those 13 billion years of travel, those galaxies are now tens of billions of light years away in terms of moving distance. And here is where the expansion becomes something more than an interesting fact. It becomes a wall. The recession velocity of those most distant galaxies, driven purely by the expansion of space, now exceeds the speed of light. Not because they are moving through space faster than light, which nothing with mass can do, but because the space between us and them is expanding so rapidly that the total distance is growing faster than light can cross it. This means we will never receive another photon from those galaxies beyond what we have already detected. The light they are emitting right now will never reach us. The expansion of space will carry them beyond our cosmic horizon before their light can make the crossing. They exist almost certainly. They burn with billions of stars. Their stars cycle through generations. Perhaps something has arisen there that wonders about the same questions we wonder about. But they are lost to us permanently and irrevocably, beyond any possible contact. Not because of any catastrophe, not because of any barrier we could one day overcome with better technology, but simply because the universe is expanding, and the expansion is winning. The distance between us and those galaxies is growing faster than the fastest thing in nature can travel. This cosmic horizon marks the edge of the observable universe. The distance to it is about 46.5 billion light-years in every direction. The observable universe is therefore about 93 billion light-years in diameter, not 13.8 billion as you might expect from the age of the universe, but much larger because of the expansion that has occurred while light was travelling. Within that sphere, astronomers estimate there are roughly 2 trillion galaxies, 2 trillion islands of stars, each separated from the others by intergalactic voids. And most of those galaxies are too far away to ever study in detail, even with the most powerful instruments we could ever conceivably build. The reason those distances are growing at all, and growing faster with every passing year, comes down to something discovered in 1998 that nobody expected to find. 2 independent teams of astronomers were studying Type 1 supernovae, stellar explosions whose peak brightness is standardized by physics, making them reliable distance markers across billions of light years. Both teams were measuring the expansion of the universe, expecting to find it slowing down over time. Gravity, after all, pulls matter together. A universe full of matter should be decelerating. What they found instead stopped them cold. The expansion was not slowing down. It was speeding up. The universe was accelerating. Something was pushing space apart at an ever-increasing rate. Both teams reached the same conclusion independently, and the discovery was so important that it earned a Nobel Prize in Physics in 2011. The name given to whatever is causing this acceleration is dark energy. It makes up about 68% of the total energy content of the universe. We do not know what it is. The simplest mathematical description treats it as a property of space itself, an energy density that is the same everywhere and does not dilute as the universe expands. Unlike matter, which thins out as space grows, dark energy maintains its strength. As the universe gets larger, the total amount of dark energy grows with it, and so the acceleration intensifies. The expansion gets faster. The distances between galaxy clusters grow more rapidly. The cosmic horizon draws in around us, slowly but relentlessly, cutting off one galaxy after another from any possible future contact. What dark energy means for intergalactic distances over the longest timescales is this. Galaxies that are today within our observable universe will begin, billions of years from now, to slip beyond our cosmic horizon. Their light will cease to arrive. They will vanish from the observable sky, not because they have been destroyed, but because the expanding universe will have pulled them so far away that no photon they emit can ever cross the growing gulf. Billions of years further still, only the galaxies gravitationally bound to our local group will remain visible. Everything beyond will be gone from any possible observation. The universe will appear to any future inhabitants to consist of just a single island galaxy floating alone in a perfectly dark sky. They will have no way of knowing about the 2 trillion galaxies that existed in our epoch. No light from those galaxies will reach them. No record will exist in any radiation they can observe. The universe will have expanded so far that its own history will be permanently hidden from its future inhabitants. That is what accelerating expansion does to intergalactic distances over the longest timescales. It makes them one-way doors that close slowly but permanently. And we are living in the last era of cosmic history when the full picture is still visible. What we can see tonight is more of the universe than anyone will ever be able to see again. Now, all of this raises a question that seems almost too basic, but is actually among the most important in all of cosmology. How do we actually know any of this? How do you measure the distance to something you cannot touch, cannot visit, and cannot send anything to in any meaningful time frame? The answer is one of the great stories of science. And it begins not with a single brilliant insight, but with a ladder. Astronomers call it the cosmic distance ladder. It is not a single technique, but a sequence of them, each one built on top of the last, each one extending the reach of measurement further into the universe than the one before it. At the lowest rung for nearby stars within our own galaxy, the technique is parallax. As the Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant ones. By measuring that shift across the full diameter of Earth's orbit, about 186 million miles, the distance can be calculated from simple geometry. The Gaia spacecraft, launched by the European Space Agency in 2013, has measured parallax distances for over 1 billion stars within the Milky Way, with extraordinary precision. It has essentially completed the 3-dimensional map of our galaxy's stellar neighbourhood, a task astronomers had worked toward for centuries. But parallax only works out to a few thousand light-years. Beyond that, the shift becomes too small to measure reliably, even for the most sensitive instruments. So astronomers climb to the next rung. For distances beyond what parallax can reach, they use standard candles, objects whose intrinsic brightness is known from their physical properties, so that measuring how bright they appear in the sky immediately tells you how far away they must be. The most important standard candle at intermediate distances is the Cepheid variable star. These stars pulsate in brightness, with a period directly related to their intrinsic luminosity. The longer the period, the brighter the star. Measure how long a Cepheid takes to complete one full pulsation cycle, and you know how bright it truly is. Compare that to how bright it appears in the sky, and you have the distance. This relationship was discovered by Henrietta Leavitt in 1912, while she was studying photographs of the Small Magellanic Cloud. Leavitt was working at the Harvard College Observatory as a human computer, one of many women hired to analyze photographic plates. She noticed that among the Cepheid variables she was cataloguing, the ones with longer pulsation periods were systematically brighter. She recognized that if all these stars were at roughly the same distance, the period had to be directly related to the star's intrinsic luminosity. Her insight transformed astronomy. It was this method that Edwin Hubble used in the 1920s to determine that the Andromeda Nebula was a separate galaxy and not a gas cloud within the Milky Way. His measurements placed it at a distance well beyond any plausible boundary of the Milky Way. The universe was not our galaxy. It was something incomprehensibly larger, For even greater distances, Type 1a supernovae are the primary tool. These are stellar explosions that occur when a white dwarf star accumulates mass from a companion until it reaches a critical threshold and detonates. Because the threshold is essentially the same physics every time, the peak brightness of these explosions is standardized across all of space and time. Type 1, a supernovae are so luminous that they can be detected billions of light years away. By measuring their apparent brightness and comparing it to their known intrinsic brightness, distances out to billions of light years can be calculated with real accuracy. And it was this technique, combined with observations of dozens of distant supernovae, that delivered the 1998 discovery of accelerating expansion, the finding that changed cosmology overnight and revealed the existence of dark energy. Above these direct distance measurements, for the most distant objects, astronomers rely on redshift combined with detailed models of cosmic expansion. As space expands, light travelling through it gets stretched to longer wavelengths. The more it has been stretched, the greater the redshift. A galaxy's redshift can be measured precisely from its spectrum by comparing the wavelengths of known spectral lines to the wavelengths at which they appear in the observed light. By combining that measured redshift with well-tested models of how the universe has expanded over time, astronomers can calculate how far away the galaxy is today and how far it was when its light was emitted. This is how we know the distances to galaxies billions of light years away, not by direct measurement, but by careful inference grounded in physics that has been tested and verified across multiple independent methods. Every rung of the distance ladder depends on the ones below it. Each step introduces its own uncertainties, but the overall picture is consistent across multiple independent approaches. And yet, threading through all of this careful, painstaking work is one of the sharpest outstanding puzzles in modern physics. It is called the Hubble tension. The Hubble constant is the number that describes how fast the universe is currently expanding, how many additional miles per second of recession speed you get for every additional unit of distance. When cosmologists measure it using the cosmic microwave background, using the physics of the early universe, they get one number. When astronomers measure it using the cosmic distance ladder, Cepheid variables, Type 1a supernovae, nearby galaxies, they get a different number, and the two numbers do not agree. The disagreement is not enormous in absolute terms, but it is larger than the measurement uncertainties on either side. Both teams have checked their work repeatedly. Multiple independent groups have done the measurements using different methods, and the disagreement persists. This matters for intergalactic distances because the Hubble constant sets the scale for everything. If it is slightly different from what we think, then every distance we calculate using redshift is slightly off. The distances between galaxies, the size of the cosmic web, the radius of the observable universe, all of these depend on getting the Hubble constant right. Most likely the resolution will require some new physics, something in our model of the early universe that is not quite right, or something about how dark energy behaves that we haven't yet understood. The James Webb Space Telescope, launched in 2021, has extended these measurements to the very edge of what is observable. It has detected galaxies so distant that their light has been travelling for more than 13 billion years, showing us the universe as it was when it was only a few 100 million years old. The earliest galaxies are small, turbulent and intensely star-forming. They look nothing like the elegant spirals and giant ellipticals we see nearby. They are the raw material of the universe, the seeds from which all later structure grew. And what the James Webb Space Telescope has found has surprised cosmologists. Galaxies in the first billion years of the universe appear more massive, more structured, and more evolved than models predicted. They look in some cases as if they formed too quickly, as if galaxy formation in the early universe was more efficient than our theories account for. And sitting behind all of these measurements, Connecting the deepest distances to the earliest moments of cosmic history is the cosmic microwave background. The faint afterglow of the Big Bang, still detectable today, stretched by billions of years of expansion into the microwave part of the spectrum. The Planck satellite mapped its temperature fluctuations in extraordinary detail, and what those fluctuations show is precisely the pattern of density variations that grew under gravity into the cosmic web we observe today. The same acoustic oscillations that produced the pattern of the microwave background also left their signature in the distribution of galaxies. The spacing of galaxy clusters today, measured across billions of light-years of intergalactic space, carries an imprint of sound waves that propagated through the early universe in its first 400,000 years. By measuring that spacing, astronomers can use the galaxy distribution itself as a cosmic ruler, cross-checking the distance ladder from an entirely independent direction. All of these methods, parallax, Cepheid variables, type 1 supernova, redshift, baryon acoustic oscillations, the cosmic microwave background, are different ways of reading the same story. The story of how the universe began, how it expanded, how structure formed, and how intergalactic distances came to be what they are. It is a coherent, consistent picture built from centuries of observation, refined by generations of astronomers, and still being sharpened today. We know the scale of the observable universe to within a few percent. The distances between galaxies are as well measured as anything in all of science, and yet the measurements themselves keep pointing toward things we do not yet understand. A tension in the expansion rate, galaxies that formed too fast, a dark energy whose nature remains completely opaque. The ladder is solid, but it keeps leading somewhere unexpected. Now let's come back to the full picture and assemble it clearly. We live in the Milky Way, a spiral galaxy about 100,000 light-years across, one of roughly 80 galaxies in the local group, which spans about 10 million light-years. The local group sits on the outskirts of the Virgo supercluster, which spans about 110 million light-years. The Virgo supercluster is one component of Laniakea, which spans roughly 500 million light-years. Laniakea is a single node in the cosmic web, surrounded by other superclusters and separated from them by voids. The KBC void, within which our local group is situated, is roughly 2 billion light-years across. Beyond the voids and filaments surrounding us, the cosmic web continues out to the limits of the observable universe, 46.5 billion light-years away. Within that sphere, there are an estimated 2 trillion galaxies, and the vast majority of the volume between them is empty. But the observable universe is not the whole universe. It is merely the part from which light has had time to reach us in 13.8 billion years. The actual universe extends beyond that horizon. It may be vastly larger than what we can see. It may be effectively infinite. There is no edge we know of, no wall, no boundary, just more space, more galaxies, more filaments and voids fading beyond our cosmic horizon into a region that will always be forever beyond our reach. Every direction you look, the universe continues past the point where its light can find you. The observable universe is not the universe, it is a window, and the window has a size set not by the universe itself, but by the speed of light and the age of time. There is something else the full picture reveals that rarely gets the attention it deserves. The fact that where a galaxy sits in the cosmic web has a profound influence on what kind of galaxy it becomes. The environment of intergalactic space is not neutral. It shapes the galaxies within it. Galaxies in the dense cores of clusters experience an environment radically different from galaxies sitting in relative isolation in the outskirts of the cosmic web. As a spiral galaxy falls into a dense cluster for the first time, the hot gas filling the intracluster medium exerts pressure on it as it moves. This ram pressure can strip the galaxy's own cold gas out from between its stars within a few 100 million years. Without gas, it can no longer form new stars. The existing stellar population continues to age. The young blue stars burn out first. The galaxy reddens, its spiral structure fades, and it is slowly transformed into an elliptical or lenticular shape. The spirals we see in isolated environments, and the red ellipticals we see in dense clusters, are often the same basic objects. The difference is not origin, it is address. Galaxies that formed in quiet filaments far from any cluster retain their gas, continued forming stars, and maintained their spiral structure over billions of years. Galaxies that fell into dense clusters had that same gas stripped away and became something different. And the galaxies sitting in the deepest voids, the most isolated objects in the observable universe, are in a sense the youngest of the old. They formed early in the universe's history, but they have continued developing ever since, protected from the violent transformation that cluster membership brings. They are bluer, more gas-rich, more actively forming stars than their counterparts in denser regions. The void is not just empty space. For the galaxies within it, it is a refuge, a place where the pace of change is slower, where a galaxy can evolve quietly over billions of years without the dramatic interruptions of mergers or the slow strangulation of ram pressure stripping. Stars can also find their way into intergalactic space entirely. During galaxy mergers, gravitational interactions can accelerate individual stars to speeds high enough to escape the combined gravitational pull of the merging system. These hypervelocity stars drift into the intergalactic void, carrying with them any planets that remain gravitationally bound. They are extraordinarily rare, but they are out there. Isolated suns and possibly isolated worlds, sailing through the dark between galaxies on journeys that will outlast any familiar feature of the current universe. Such a world would be frozen, receiving no starlight, warmed only by the residual heat of its formation billions of years ago, and perhaps by the decay of radioactive elements in its interior. Its sky would be almost perfectly dark. No sun, no sibling planets, no neighbour stars. Just the distant galaxies, each one a faint smudge of light, and the absolute cold of intergalactic space stretching in every direction without end. If any form of life ever arose on such a world, its entire understanding of the cosmos would be built without the anchor of a nearby star. It would look out into a sky of only galaxies. Its sense of scale would be different from ours. We built our concept of cosmic distance from the inside out, starting with the small and working toward the large. A civilization on an intergalactic rogue world might begin with the large and work inward, if they ever found anything to work inward toward. In a strange way, that might give it a more accurate intuition for the true scale of things than we have ever managed. We are insulated from the reality of the universe by our galactic address. Living inside a galaxy is, cosmologically speaking, a highly atypical environment. Most of the volume of the universe is void. Most of the volume of the universe contains almost nothing. The galaxies, the stars, the planets, the life. All of it exists in the tiny fraction of space that is not void. And that fraction is shrinking in the only way that matters. Not because the galaxies are disappearing, but because the distances between them are growing. Dark energy is widening every void, lengthening every intergalactic gap, pushing the cosmic web's components further apart with every passing year. The local group will eventually be all that remains visible to any observer within it. The Virgo cluster will recede beyond the horizon. The Shapley supercluster will follow. One by one, the landmarks of the cosmic web will slip away, not violently, not suddenly, but slowly and irrevocably, carried beyond the reach of any signal, any telescope, any contact of any kind. The universe will not end. it will simply become unreachable to itself. What remains, over the longest time scales the universe permits, is isolation. The merged remnant of the Milky Way and Andromeda, already given the name Milkomeda by astronomers who have simulated the collision in detail, will float in a universe that appears from any telescope within it to contain only a single island of stars. No evidence of the 2 trillion galaxies that once filled the sky will remain in any radiation any instrument could detect. The universe's own history will have been erased not by destruction, but by distance, by the simple, patient, unstoppable expansion of space, widening the gaps between things until the gaps become everything. We live in the last era of cosmic history when the full picture is still visible. The universe is old enough to have formed rich, complex structures, galaxies, clusters, superclusters, the entire architecture of the cosmic web. But it is not yet so old that dark energy has stripped the observable record away. The 2 trillion galaxies are still out there, still sending their light toward us, still reachable by the right telescope pointed in the right direction on the right night. That will not always be true. The window is open now. It will not stay open forever. There is something worth sitting within that. We are small. Our galaxy is small. Our local group is a rounding error in the volume of the observable universe. And yet we are the part of the universe that looked out into the void and began to understand it. That looked at the distances between galaxies, the incomprehensible, defeating, irrevocably large distances, and tried earnestly and persistently to comprehend what those distances mean. Not just to record the numbers, but to feel their weight, to follow the logic from the familiar to the unfamiliar until the unfamiliar becomes, if not imaginable, then at least honestly known. So the next time you look up at Andromeda on a clear night, that faint smudge of light near its constellation, barely visible to the naked eye, remember what you're looking across: 2.5 million light-years of near total emptiness. A gap so vast that our entire galaxy is a rounding error within it. And remember that the light reaching your eye tonight left its source before our species existed, before our genus existed, before anything we would recognize as human had yet appeared on this planet. It crossed all of that distance, through all of that void, through a universe that was expanding the entire time, and arrived here, at your eye, tonight. The universe is larger than our minds were built to hold, and that is true and real and worth knowing. The distance between galaxies is not just a number, it is the most honest measure we have of what the universe actually is. If you liked the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.